Welcome back to ECE 442-542. Seems like we've been gone a year, but it's only been a week, I think, right? And you've been busy, I hope, watching all these supplementary videos and reading up on the notes. Homework number 5 is due on Monday. Project deliverable number 1, which is a paragraph description of what you're going to be doing in your project for ECE 542. That is also due on the 1st of April. If you have stepped away from the class, you may not have noticed that there's another submodule inside Unit 5, and it contains all these S's. These are supplements. We have a supplement to 5.2. Actually, we have 3 supplements to Lecture 5.2. The first of those is talking about or discussing how do you create this transfer function T sub C of S, and that's consistent with some of your first 2 homework problems on homework set number 5. What happens if you have competing performance specifications? That's the second supplement for Lecture 5.2. And then the third is this relationship or connection or illustration of sampling, frequency, aliasing, Nyquist rate, etc. That's supplement number 3 for Lecture 5.2. There's a supplement for Lecture 5.3, and that's an overview of controller design. If you haven't ever taken a control class, it might be helpful to see or to look at that particular material, and now you're seeing it in a context of this course. What is not yet there, which I think needs to wait maybe until after today's material, is Supplement 5.5, which deals with the Ragazzini design example and something known as intersample ripple. And that might really pique your interest to know what in the world is intersample ripple. But essentially you can think of that as bumps and dynamic behavior or interesting behavior between samples. And if you just looked at the values at the sample points, you might think, oh, at this particular sample I was at 1, and at the next sample I was at 1. But in fact, in between that, if you looked at the continuous time waveform, you might have some ripple between those 2 points. Just saying, there's some interesting things that can happen in discrete time control beyond just looking at what's happening at the particular values at the sample points. And the Ragazzini design, it may not be the best design approach, but it does provide you with the background on some of these issues that you need to be concerned about. And in particular, we better not cancel poles and zeros with our unstable poles and zeros with our controller. And that's brought out in the Ragazzini design example. There is reading material in Unit 5. If you want to read a more textbook type description of the Ragazzini design approach, that's available within Unit 5 on D2L. There is also exam number 3 material, which I'm not sure if I hope you're planning ahead. Exam 3 is in 2 weeks. That's on Wednesday, the 10th of April. And right before that, we will have a review session if you think that's going to be beneficial. And if you're interested in submitting questions or topics for that review session, which will be held immediately following the Monday lecture on the 8th of April, you can submit that information on the quiz associated with that on D2L. Homework 6 is due on that Monday before the exam. And again, the exam is 2 weeks from today, exam number 3. After that, you have a project and a final and maybe a couple more homework assignments. Wow. And then the semester will be over, at least for you guys, right? Someone will have to grade some of that material. Here's what I am planning for, this is what I'm calling Lecture 5.4. Lecture 5.5 is the Ragazzini example with the intersample ripple illustration. Today, what I want to do is basically really set up. How many are finished with homework number 5? Oh, if you're finished, then maybe you can help me work through these hints and help. But if you're not finished, I'm going to sort of help you get through that. And hopefully, if you've already worked it, what I'm telling you is consistent with what you did. If it's not, you still have time to modify your work or update me if I'm in error. Then we'll look at why do these restrictions with the Ragazzini approach, where do they arise, or the justifications for those. And we have 4 restrictions that we talk about with the Ragazzini approach. And those 4 restrictions do not always have to be existing. You might have restriction 1 and 2, and that's it. Or maybe you have restriction 1 and restriction 4 that you want to worry about, and restrictions 2 and 3 aren't even pertinent to that particular design because your original system may not have any unstable poles or unstable zeros. Restrictions 2 and 3 are only going to arise or be of concern when you have restriction 2, when you have unstable zeros or zeros outside the unit circle. That's what I'm meaning by unstable zeros. Restriction 3 comes into play when you have an unstable system or the poles in your system G of Z are outside the unit circle. After that, we'll talk about a PID controller, give an overview of that, what the P, the I, and the D correspond to. That's proportional, integral, and derivative action based on the air signal in your system. And those 3 parts can be combined, looked at separately, looked at in pairs, etc. We will actually look at proportional control, and that will then say, oh, what can we do with just a gain? And based on that, we can find out what values of gain actually provide a stable closed-loop system, and that should naturally lead us into what's called a root locus design or a root locus diagram that shows closed loop poles relative to adjusting a parameter. And in this particular case, that parameter is our gain, K. And we could actually set this up to where G bar of Z might already incorporate some integral terms or a derivative term, and we now have an adjustable parameter. And we're maybe doing more than just proportional control, but you can view it as if you were just adjusting a parameter K in your closed loop system. Let's get started with hints and help for homework number 5. Relative to problems 1 and 2, you are essentially given performance specifications or particular properties that you want your closed loop system to achieve. And in that particular case, what you're after or really looking for is what does the denominator polynomial, what should it look like? And essentially, what are alpha sub 0, what's the constant, and what's the linear term in this second order polynomial or in this quadratic polynomial? And I believe most of the problems, if not all, or all of the parts of those, assume that you have a 0 at the origin. That's where the Z comes in. And now maybe you adjust the K or manipulate the K to try to establish, let's say, DC gain or steady state accuracy characteristics. And to find what alpha 0 and alpha 1 are from the performance specs, you should be able to go back and look at lectures 5.1, 5.2, and supplemental lecture 1 relative to lecture 5.2. I hope the notation is clear what I'm trying to say with those supplementary pieces or lecture parts. When we talk about settling time, one of the performance specifications, you should be seeing circles, concentric circles, and how do we then determine what that radius is? Well, that's usually based on, or what the value R is associated with a couple of poles. What's the distance those poles are from the origin? That's R, and that usually is based on a 1% settling time, where the 1% settling time is R to some settling time integer value, capital N settle, and when does that quantity equal or become less than 0.01. The first time it becomes less than 0.01, or your trajectory gets less than 0.01 and stays less than 0.01, that's the value of the sample settling time, sample distance in settle. And you can solve based on R to the N equal 0.01, you can solve that for R to obtain the radius that you need, given a particular settling time quantity, either absolute time, which is T sub settle, or the number of sample periods to settle, which is capital N sub settle. Let me ask you some questions just so that you're maybe staying clued in to what I'm talking about. If we want a shorter settling time, then going to the right after the shorter settling time, that implies a smaller or larger circle around the origin in the z-plane. And now what I want you to do, I guess, I should have put larger on top and smaller down below. Thumbs up is larger, thumbs down is smaller. We okay with that at the count of 3? All right, so larger is up, smaller is down, which isn't this consistent with my picture or wording. 1, 2, 3. So if we want a shorter settling time, if we want to go from maybe a settling time of 10 seconds to a settling time of 5 seconds, that should correspond to a smaller circle around the origin. So your thumb hopefully was down on that. And a shorter settling time. Now if we go down, oh, I still did slower up top and faster down. So faster is thumbs up, slower is thumbs down. A shorter settling time means what? A shorter or a slower response or a faster response. The count of 3. 1, 2, 3. What did I say? I'm confusing myself now. Thumbs up was faster, right? It should be a faster response if you have a shorter settling time. So hopefully you had your thumb up on that to get a faster response. Is course, when I say a shorter settling time, I'm meaning a faster response, or I'm meaning a smaller circle around the origin in the complex z-plane. So if we look at this diagram in the complex z-plane with two circles, an R1 circle and an R2 circle, with R2 being interior to R1, then R2 is obviously smaller than R1, and that R2 produces a, just tell me, since I couldn't follow thumbs, faster or slower response versus R1. R2 produces a faster response than R1 does. And those are the kinds of questions you need to be thinking about relative to problems 1 and 2. Where do you locate these triangles, these dominant triangles? A lot of those will have some angle theta sub d, which isn't indicated here on the diagram. But I might give you a problem that doesn't specify an angle? What's the angle provide for us? Or how do we typically end up with a specification on the angle theta sub d? What's that corresponding to? Does peak time give us something like that, or overshoot? Those should, what's the overshoot give us? Be still my heart. The percent overshoot is relative to the heart shape, and the theta sub d is usually, or the wedge is associated with the peak time. How fast are you reaching your peak? If you're not given either of those, percent overshoot or peak time, now what do? How do you pick a theta sub d? Do you punt? Or just drop the ball? Or pass it to someone else and hope that they know how to work the problem? If there's nothing explicitly contained in the constraints, you may want to just say, let me make this as simple as possible. Let me make my poles real. If I don't have to worry about a percent overshoot or a peak time, maybe I just make my poles real, and I just need to make that real distance a value of r away from the origin, where that r now satisfies the settling time specification. Meaning if you're now struggling saying, well, he didn't give me a theta sub d, well, maybe you won't be given a theta sub d. Maybe all you need to worry about is settling time. But if nobody gives you a theta sub d and you want a theta sub d, if you just have to have it, what's a Goldilocks value for theta sub d? That's a misleading question, actually. In the continuous time setting, theta, which isn't theta sub d, in the S-plane you want an angle of 45 degrees, which corresponds to a zeta of 0.7. So now you're looking for a heart, or the logarithmic spiral, associated with zeta of 0.7. If you wanted just to pull a zeta out of the air, you might say, well, that gives me a good trade-off between peak time and percent overshoot. That's a pretty good value of zeta. You probably don't want to just pull something out of the air and say, oh, I want a theta sub d of 120 degrees. Somebody might say, well, where did that come from? I don't know, I just picked it. Well, you probably want to have a rational reason or an explanation behind where that theta sub d might be coming from. That's problems 1 and 2. Problem 3 maybe wasn't stated explicitly, and so now I'm telling you, let's go ahead and assume a zero order hold equivalent to obtain a g of z. I believe the original problem was design a controller to stabilize a system that has a g of s equal to 1 over s minus 1, or it's an unstable system. We have a pole in the complex S-plane at s equal to plus 1. Now you want to take that into a g of z, and we have this expression that will do that. We now have 1 minus z to the minus 1 times the z transform of g of s over s. G of s was 1 over s minus 1. And we divide that by s, and now we have a pole at the origin and a pole at s equal to plus 1. And what we're doing is we are now putting all three of those boxes on the right-hand side. We're incorporating a zero order hold with our plant g of s. The a to d on the output side of that doesn't impact the dynamics, but all three of those together give us our capital G of z. You could do that manually, or you could just wait until I scroll and show you how you might do it on MATLAB. If you did it on MATLAB, you could now take the original underlying system, capital G of S, which is 1 over S minus 1. That's unstable. It'd be nice if you could now stabilize that with maybe a computer-based controller, an Arduino. You now have an unstable system and you want to control it to at least stabilize it. The first thing you want to do is put that system into an object in MATLAB, and you can do that with the TF command, the transfer function command in MATLAB. You put the numerator polynomial in first of the two arguments, and the second argument is a vector associated with the denominator polynomial. In this example, our numerator is pretty basic. It's just a constant of 1. But if it was a cubic, you could put that polynomial in as a vector, a row vector, of 4 different coefficients, with the highest, or the coefficient on the left corresponding to the coefficient of the s cubed term, and the s to the 0 coefficient would be at the rightmost side of that row vector. Consistent, I hope, with how I've described or represented the denominator of capital G of S. It's now S minus 1. I put in minus 1 on the right-hand side, and I keep working my way to the left in that row vector until I run out of powers of S. And there's only S in there, so now I have to just have a 2 vector to represent S minus 1. First coefficient of S, the leading coefficient, that's a monic polynomial. It has a coefficient of 1, so I have left square bracket 1 comma minus 1. That's now G sitting in MATLAB. There's another function in MATLAB, C to D, and it defaults to the 0 order hold equivalent. If we now plug in the G object, that transfer function, into C to D, and include the specified sample period of 0.1, what will end up happening is it will generate a transfer function by default that assumes the 0 order hold equivalent. And that's now what is sitting there in the blue box, capital G of Z, and that now should be what you could use in your design for problem number 3. Now you could say from MATLAB, G of Z, or you could show these little steps, and that's probably what I would do if you don't want to do anything more. At least you now know where that came from if somebody's asking you to explain your homework problem 5, or if you're now trying to figure out what you did in a couple of years, you might say, oh, I was just in MATLAB and I had to do these 2 functions. What you want to do with G of Z is extract or identify some of the useful information. Restriction 1 in the Ragazzini design worries about the pole 0 excess. Here the pole 0 excess of our original plant, that capital G of Z, is 1. The numerator is just a constant. The denominator is a first order polynomial. So that says what we need to have for capital T sub C of Z as far as its pole 0 excess. That's restriction 1. Is restriction 2 in play? Based on the way that we've ordered the restrictions. And I just want to keep those restrictions in that order. Not that you have to worry about memorizing exactly which one is which, but I think for this class, so that we're all speaking this together, we'll do R1, R2, R3, and R4 in the order that I've labeled them. Is R2 active? Do we have the second restriction for this G of Z? What does R2, restriction 2 in the Ragazzini design refer to? That deals with zeros in your plant, G of Z, and if those zeros are outside the unit circle, then restriction 2 comes into play. We don't have any zeros, And so they're obviously not outside the unit circle. We don't have to worry about restriction 2. What about restriction 3? Restriction 3 concerned unstable poles in your original plant, G of Z. Is that in effect for this problem? Are the values of Z in the denominator, is one of those or more of those outside the unit circle? Yes. So this plant is unstable, which is good because what? We started with an unstable analog plant. We better keep that unstable plant when we go from continuous time to discrete time. This G of Z is now consistent with what we had for G of S. We do have a pole outside the unit circle. We need our pole zero excess to be 1, and maybe in problem 3 did I say you want the response to be deadbeat? What in the world is he calling deadbeat? But deadbeat is really you just beat the response to be nothing or dead after a finite number of sample periods. In this case, you will quit moving after 1 sample period because you just have 1 pole at the origin. If you had 3 poles at the origin, then you would have a deadbeat response, but it would take 3 sample periods before it would become 0. That's what it is meaning by deadbeat. Question?
I just had a question about the pole zero excess. So in the notes it said that the transfer function had to have at least the same pole zero excess as G. Can it have a larger pole zero excess, or does it have to be the same?
The question was, the wording on the restriction 1 said that the desired closed loop, or T sub C, has to have a pole zero excess of at least the same magnitude as your original plant. So the key word is at least. You could have a larger pole zero excess if you want. There might be design reasons for doing that, meaning maybe you want a second order denominator and a constant numerator for a system that might be like G of Z here. That maybe wasn't asked for, but let's say that you try this T sub C of Z in a real scenario, and now you start simulating the results after designing your controller, and you go, you know what, I'm not real happy with this controller. Maybe I need to make T sub C of Z have a little bit more flexibility in what T sub C of Z provides for me. And now you might want to put a couple of poles. If they're both at the origin, then you just would have a Z squared in the denominator if you still wanted to maintain deadbeat response. But now you could put another numerator factor in there, and that might give you an additional parameter to play with. If you said, oh, I want to preserve a pole zero excess of 1, and now my denominator is Z squared, oh, I could now have in the numerator K times the quantity Z minus alpha. Now you have a K and an alpha to play with to maybe help you achieve behavior that you're more likely to agree with. That's problem 3. Did that answer your question on the at least? So you can have a pole zero excess of, in that case, 1 or more, but it has to at least be the same size as your original plant. Problem 4. I think I give you this transfer function, G of Z, and with this G of Z, the pole zero excess, what is it? These are really, really, really challenging questions, so maybe I'll give you about 30 minutes to, no. So you should be able to instantly see what the pole zero excess of capital G of Z is and fill in the blank. What is our pole zero excess? It's just 1. And that says then, based on restriction 1, says T sub C of Z must have a pole zero excess of at least 1. And we could have a pole zero excess of 2 or 3 if we wanted, but at least a pole zero excess of 1. In this G of Z, do we have any unstable factors? Do we have any zero factors or pole factors that are unstable? And I could, on the third exam or on the final, give you maybe 2 unstable zeros or 2 unstable poles. In the homework, we've been focusing on just 1, but you never want to discount too many possibilities. But G of Z has an unstable. Is there anything unstable in G of Z? And here it's really not, it's a little misleading saying an unstable 0. That doesn't cause your system to be unstable. It's just a briefer way to say, oh, I have a 0 outside the unit circle. Instead of saying all of those words, I can just say an unstable 0. Is that okay? It's not really causing your system to go unstable by itself, but typically having zeros outside the unit circle makes your job of controlling that system more difficult. A system with a 0 outside the unit circle is more challenging to work with than when you have all of your zeros inside the unit circle. Talking about zeros, but I could have been, well, if they're unstable poles, that does cause, if you don't control the system and it's an open loop system, you excite that system, it's going to go unbounded, your output response, if you have poles, any pole outside the unit circle. So in that sense, an unstable pole is an okay use of that word. G of Z has an unstable pole or 0 is what I'm looking for. In this case, it's the 0 that's unstable. And which restriction does that now put into play? Based on our ordering or definition, it's restriction 2. And you could have all 4 restrictions active in one problem. You could have an unstable system, or that means an unstable pole. You could have an unstable 0 or a 0 outside the unit circle. You could have a steady state accuracy specification, that's restriction 4, and by default you have restriction 1, which is concerned with the pole 0 excess of your closed loop system. So now we have restriction 2, and what does restriction 2 mean, or what does that impose on our system design? It's called a restriction. What does it mean? Restriction 2. If restriction 2 is in play, what do I now have to do? Restriction 1 says I have to have a pole 0 excess of at least 1 in T sub C of Z. Restriction 2, does that deal with anything in T sub C of Z? Now I need T sub C of Z to have some particular property, and this one actually is the most straightforward of the restrictions of restriction 2 and 3. This one you just have to put those unstable 0 factors, include those in T sub C of Z. That means that we need to force a Z minus 1.1 factor in the numerator of T sub C of Z. And I probably said in problem number 4 I want a deadbeat response, so I'm putting all of my poles at the origin. But what's in this cloud, since everybody goes to the cloud for a lot of answers these days, now that cloud is the exponent on Z. What's in that cloud? 1, 2, 3, 4, 5, 6, 7. So now I could be, what does it have to be? It has to be 1. It has to be 1. Where'd that come from? I don't know. Anyway, does it need, is 1 okay? What's our first restriction? Tell us. What did we want from restriction 1? We need a pole zero excess of at least 1 in T sub c of z. So we need it to be at least 2, don't we? And we could have gone to 3, we could have gone to 4, we could have gone to 5, but there may be no reason to do that unless we have additional behavior or performance requirements or accuracy requirements that we're trying to achieve. And in that case, we might want to put some more zero factors in. But here, let's keep it right now as basic as we can. And in that case, let's just say that we put a 2 in there. Now we have a pole zero excess of 1. We have our unstable factor from restriction 2. Now we've fixed our poles in our denominator to have a deadbeat response. But do you see that I could make this design a little bit more algebraically messy by giving the denominator certain performance specifications like a settling time, a percent overshoot, and a peak time? Now you would have problems 1 and 2 combined with this to give you the denominator properties that you want. That being said, what are those performance specifications relative to circles, hearts, and wedges? Just to keep in mind. What did we say, or how did we preface that discussion when we started talking about our shapes? So now I want you to pull out your mats, lay down on the floor, and we're going to play with shapes. We're going to play with circles, wedges, and hearts. But what do we know about those shapes or their relationship to performance specifications? Now if you're at home, you may not be getting the signals that I'm sending, but those are really just guides or rules of thumb. Because if we now start having zeros in our closed loop transfer function, capital T sub c of z, those start to influence and impact the transient behavior, and you may design and you go, well, I picked my theta sub d and my r to give me a percent overshoot of 10%. What happened, Tharp? Now I have a 50% overshoot. Well, it might be because you have zeros in your numerator that we didn't consider when we were talking about these dominant poles related to performance specifications. So don't hang me out to dry too much when you see that your performance specifications are not consistent with what you thought they should be. Because if your T sub c of z gets a little bit more complicated than just a 0 at the origin and all your denominator polynomials, then things might look a little weird relative to the performance specs. They're just guides. They're just rules of thumb. The only thing left really now is the choice of k in problem number 4. We fixed our numerator. We fixed our denominator. We can use k as a design parameter. And one option, if I force capital T sub c of z to equal 1 when z is equal to 1, what's that mean? What does that say? That's the DC gain. That's giving us a DC gain of 1 because we're evaluating it at z equal to 1. That's now a frequency of DC in the z-plane. We're saying, oh, let's pick k to give us a DC gain of 1, which means if I put in a 4 to my system, after the transients are gone, my output better be 4. So this is now a DC gain specification. And there may be other reasons for picking k. You might want to put in another, if I now put in another 0 factor, suppose I now put in a factor that was like this. Now I have an alpha and a k to play with, but what do I need to adjust anything else before I move on to try to find my c? Yes, I have to preserve my pole 0 excess. So I would have to put in another pole, and if I wanted my deadbeat response to be preserved, I would put another pole at the origin. Now my pole 0 excess remains 1, and I'm okay. But I now have more flexibility. I now have 2 parameters to adjust or play with if that provides me with any additional or useful information. Questions on the homework help or hints? Those that have already completed, I think the majority had already finished homework number 5. Were those consistent with what you'd done? Yeah, okay, I see a lot of heads shaking yes. Actually, there's a jar at the door as you leave, the tip jar for all those helps and hints. If you want, just saying. And if you're at home, the address is. Okay, anyway. Ragazzini restrictions. Here's our design formula. And in a minute, we're going to actually derive that. We haven't derived it yet, have we? Where that came from. I think I just gave it to you. We'll derive that, although you've probably already derived it. But I want to now identify some of the restrictions or how they can be connected to this design formula for the controller C of Z. The first one that I've already identified is I've said that 1 minus T sub C of Z, that's the denominator, one of the pieces of the denominator package that's creating capital C of Z, that's proper, meaning the numerator degree is the same as the denominator degree. And that's by construction. If I say 1 minus some rational expression, and if I get a common denominator, the 1 minus, the 1 is going to have a numerator and denominator equal to the denominator of T sub C of Z. And now if I combine that numerator with the minus numerator of T sub C of Z, its polynomial is the same order as the denominator polynomial in T sub C of Z. It's proper, which means that I'm not changing the pole 0 excess by that factor 1 minus T sub C of Z. The numerator and denominator in that piece is the same, order-wise. But now if I preserve the pole 0 excess in G of Z with T sub C of Z, or I have at least the same pole 0 excess, I'm not going to make a non-causal controller. Let's now look at some of the other restrictions. And I'll go through restriction 1 maybe a little bit more in just a minute. But restriction 2 dealt with what? The unstable zero factors in the original plant. Can I maybe make those? So I'm cutting G of Z into 2 parts. I'm putting a numerator part and a denominator part, and I've now circled the numerator expression in G of Z. What do I want? I do not want my controller to possess poles that would cancel unstable zeros. Now, okay, first let me go back. What is this controller doing? What is 1 over g of z in that expression for the controller doing? If you just had to interpret, forget the t over 1 minus t for a minute. What's 1 over g of z doing in your controller? And think about where the controller is. You have c of z times g of z in your block diagram. What's this 1 over g of z actually trying to do? It's basically canceling your plant, is it not? It's saying when I multiply g of z and divide by g of z, I get 1. So ideally, your controller is trying to cancel the dynamics of your original plant. So that 1 over g of z is saying, I'm trying to cancel, and then I'm going to give you back what you want, ideally, and that's what the t sub c over 1 minus t sub c gives us as our ideal closed loop behavior. But what we want to make sure is when we finally end up with a controller, c of z, we better not have that controller canceling unstable pole and zero factors in our original plant. So to avoid that, what we're doing is we're making sure that those factors do not appear in the appropriate location in c of z. Meaning, if we do not want c of z to have poles that would cancel unstable zeros in g of z when we multiply g of z by c of z, then we want to make sure that those unstable numerator factors in g of z are in fact canceled by a consistent factor in t sub c of z, and then they won't be in our controller, capital C of z. So this is restriction 2. That says that I'm going to make sure that my unstable zero factors are not going to be pole factors in c of z, which they would be if my t sub c of z didn't have the same unstable zero factors that g of z has. And I would, by inverting the plant, I would basically be trying to cancel unstable zero factors with this 1 over g of z. The same argument, or a similar argument, goes for unstable zero factors in g of z. We now want to make sure that we have 1 minus t sub c of z evaluated at those unstable locations being equal to 0. And that will then cancel those unstable factors in the denominator of g of z. So this is now restriction 3. That's how you can sort of think about restriction 2 and restriction 3 as indicated in your design formula. They take care of themselves if you set it up right. That's where those are coming from. Let's now look at restriction 1 a little bit more carefully, the background behind restriction 1. Restriction 1 dealt with the pole zero excess. Where the pole zero excess in capital G of Z the pole zero excess in G of Z will result in poles at infinity in C of Z unless T sub C of Z possesses at least the same pole zero excess as our original plant G of Z. And you're going, what? I don't even know what he's talking about. Poles at infinity. What are poles at infinity? What are poles? If you had to describe a pole, what does that correspond to in terms of your transfer function's behavior? What happens at a pole? Your transfer function goes unbounded, doesn't it? Now, if we have poles at infinity in our controller, that really means that we have a numerator polynomial that exceeds in order or power the denominator polynomial. Meaning as z goes to infinity, that numerator would go unbounded. Let's say that we had a c of z that was equal to z. Its numerator is first order, its denominator is a constant 1, it's 0th order. As we look at capital C of z equal to z, it has a pole at infinity. It goes unbounded as z gets big. Is that clear? And what does C of z equal to z correspond to in terms of behavior? Suppose that we now said something like the following. The input to the plant, U of z, is going to be C of z times E of z. That's what's happening in our block diagram. We take the air and we manipulate it through this controller, C of z, and produce the input U that drives our plant in the block diagram. What happens now if capital C of z had a pole at infinity? Can you now take this into the time domain? What happens now when we inverse C transform the left side of that equation? What do we have? Don't we just get U of n? What happens when we inverse Z transform the right-hand side? We now have E of n plus 1. Now the input is dependent on an air signal that's in the future. It's non-causal. And that's due to having a pole at infinity. So poles at infinity in C of z cause a non-causal property in our controller. That's what this little example was supposed to illustrate. Again, we're talking about restriction 1, which is making sure the pole zero excess in T sub C of z is at least as big as the original plant's pole zero excess. So this restriction on the pole zero excess in our desired closed loop transfer function, T sub c of z, I hope makes sense. Suppose that g of z had a pole zero excess of 1. And you've already seen plants that possess that property in today's lecture. If we now have one more pole than we have 0, what do we know about g of z in terms of its input-output behavior? Then g of z would have a 1 sample period delay between the input and the output. Suppose we had a g of z that was 1 over z. Pole zero excess of 1, right? Or this is now z to the minus 1, which means that y of z equaling g of z, let's say u of z, has what relationship in the time domain? We inverse z transform the left, we have y of n. We inverse z transform the right-hand side, and if it's just z to the minus 1 u of z, that's now u of n minus 1. That's what I'm meaning by, this is a very simple example, but that's what happens if we had a plant that had a pole zero excess of 1. We would have a unit delay if that was how simple our plant was. So now we have a 1 sample period delay between the input and the output. Forcing our desired closed loop transfer function, T sub c of z, to have a pole zero excess of 1 means we are forcing T sub c of z to have at least the same amount of delay as the original plant. To have at least the same amount of delay as the original plant g of z. And now you can work through that if you wanted to. Now you have y of z is equal to T sub c of z r of z. And by ensuring that T sub c of z in this formula, 1 minus T sub c of z is not going to change the pole zero excess because it's proper. That's what I'm meaning by circling it and saying it's proper. So now we're comparing the pole zero excess of T sub c of z with the pole zero excess of g of z. As long as T sub c of z has at least the same pole zero excess as the original plant, we will preserve or produce a causal controller. will have at least as much delay in the desired closed loop transfer function T sub c as what we have in the original plant. That's the reason for having a pole zero excess of at least the same pole zero excess in our original plant. Let's now derive that controller design formula in the Ragazzini approach. C of z is equal to 1 over g of z. So ideally we would invert the plant, that's a way of thinking about it, with our controller, and then we would replace that inverted plant with a transfer function in our controller that makes the whole closed loop dynamics, or the whole closed loop transfer function, equal T sub c of z, which is what we want. Our goal now in this short derivation is to find the controller which we're calling capital C of z, that realizes or produces a closed loop transfer function equal to T sub c of z. We want the transfer function between our reference input R and the output Y to be T sub c of z. And we're assuming this classical block diagram configuration. There's our plant. Here is our controller. And they are interconnected in a unity output feedback configuration. Here's R of z, and there's Y of z. And if we need it, which we might, here's E of z, the air signal, and here is the input to the plant, U of z. Let's now see if we can, based on this configuration, show that a C of z needs to equal this in order to have the closed loop transfer function between R and Y being T sub c of z. What's Y of z in terms of this block diagram representation? And if we don't want, if you remember the cheer, you're already done from a previous semester. But suppose we don't. Let's write Y in terms of the air signal E. So now we're saying, oh, we need to figure out what Y is in that chain, or in that particular highlighted path. So now we see that Y of z is actually G of z times C of z. Those are all transfer functions times a signal, E of z. Just block diagram algebra. But what is E of z? E of z is just R minus Y. E is the output of that summing junction. E of z is now R of z minus Y of z. And we know what Y of z is. Y of z is G of z, C of z. I'm going to suppress the arguments on those, times E, which is R minus Y. Simply combining those previous two expressions. And now we have one equation that possesses a signal R and it possesses a signal Y. We can now do the algebra on this to find our desired closed loop transfer function, T sub C of Z. This now says that if we distribute that GC through on both terms on the right and add the term associated with Y to both sides, we end up with 1 plus GCY equaling GCR. And dividing that factor that's scaling Y through on both sides, we end up with Y of Z is equal to G of Z, C of Z over 1 plus G of Z, C of Z. Now we have an expression for T sub C of Z in terms of C and G, and we want to basically reverse that process to see what C of Z equals in terms of T sub C and G. Hopefully you believe that this is what we have from the block diagram. This is what T sub C of Z is equal to. If T sub C of Z is in fact equal to G of Z, C of Z over 1 plus G of Z, C of Z, then we should be able to solve for C of Z. To do that, first let's get rid of the fraction. Or let's multiply both sides by 1 plus GC. Distribute the T sub C across the two terms on the left, and we have T sub C plus GC T sub C is equal to GC. And what are we trying to do? We're actually trying to now pull out C of Z from this expression. So let's first subtract C, or let's get all the terms that involve C on the right-hand side. So we now have GC minus GC T sub C. And we're assuming these are scalar transfer functions, so we can slide them around. They commute. GC and T sub C we can slide around. So let's now factor out a G from the left and factor out a C from the right. And what do we have in the parentheses? We had a GC term, and we can get that by just including a 1 there. And then we had we okay with that. Or now we have the relationship that we really are looking for. We now see that T sub C is G times 1 minus T sub C, C. And now we can simply divide the G and the 1 minus T sub C factors through on both sides and end up with an expression for C. So that now we can say, oh, that's our C expression. C of Z is now a 1 over G of Z. And what does that do? Well, that tries to invert the plant. And then we have a T sub C of Z divided by 1 minus T sub C of Z. And there is our controller design formula. That's the direct controller design formula. That's where that came from. So whenever you see this Ragazzini design and you're trying to apply it and you say, well, now that I have all these restrictions in place, let me just create my C of Z. Boom, you can just turn the crank based on this formula and you'll obtain a controller. What we haven't yet talked about maybe too much is restriction 4, which is dealing with steady state accuracy. Restriction 4 might say that we want or we have steady state accuracy may impose additional constraints on T sub C of Z as Z goes to 1. Let's see what, or if we can sort of obtain a feel for this based on a straightforward example. If we now look at the error in that previous block diagram, that was the reference signal R minus the output Y. That's E of Z. But we know what Y of Z equals in terms of, or as a function of R. That's just T sub C times R. So this is now minus T sub C of Z, R of Z. So now we see that E of Z is in fact 1 minus T sub C of Z times R of Z, the input. Suppose we want zero error due to a constant reference input R of Z. What would R of Z look like in the frequency domain if it's a constant? It's now AZ over Z minus 1. And we can now apply the final value theorem to see what happens to the error signal if we're trying to obtain zero error due to a constant input. And the final value theorem yields the following. We now say that in the time domain, as n, little n, goes to infinity, in our error signal E of n, the final value theorem says that that's can be found by looking at the limit as z goes to 1 of z minus 1 times E of Z. Well, we have an expression for E of Z. Let's plug that in. We now are looking at the limit as z goes to 1 of z minus 1. E of Z was 1 minus T sub C of Z times R of Z, which was AZ over Z minus 1. These two cancel, and if we want this to equal 0, what's that impose? As z goes to 1, do you see that we can now look at what t sub c must equal as z equals 1? It has to equal 1. So now we're saying, or we see, that that steady state accuracy spec produces the limit as z goes to 1 of t sub c of z equaling 1. Or t sub c of z evaluated at z equal to 1 equaling 1 is a steady state accuracy spec, and that says that we now have a DC gain of 1 of our closed loop system. And if we needed more, we could maybe talk about accuracy to a ramp, etc., and that might impose additional constraints on t sub c of z. So we'll pick up at that point next time, which is, Monday, which is when your homework is due.